Okay, so here we're looking at the cathode ray oscilloscope. Okay, CRO. Now, what is a cathode ray? A cathode ray is essentially just a beam of electrons. Okay, so a whole lot of electrons flying through the air. Cathode refers to negative, anode refers to positive. Okay, so electrons are negative, that's what it refers to. So here we've got a tube, it's a vacuum, so this thing is a glass tube and inside is a vacuum. You have a hot element, okay, and so if you have a hot element, you make this thing hot, then little electrons will actually be ejected, okay, because you're giving them energy, kinetic energy, and they will get out, okay. Now, if you actually have this thing here, which is positive, an anode, then the electrons will accelerate. So what they say is accelerate towards that anode. And this makes an electric current, and that acceleration will increase the current. Now, no current will flow if the filament is not heated, and there is no voltage to attract it. Okay. Now, electron beams or cathode rays can be deflected by electric and magnetic field. Okay, so if you have an electric field, let's say this was a positively charged plate. Okay, you attach that to a positive end of a 20,000 volt battery, and the other one is negative. Now, if we fire an electron, so there's my electron, okay, and we fire it into this thing, goes straight, and then once it hits the space between these magnetic fields, electric fields, it will curve in a parabolic path. Then once it's outside, it then goes straight again because it's no longer under the influence. Now, how does it react to magnetic fields? Let's say I had a magnetic field going into the page of this paper. Okay, going away from me. Remember the back of an arrow, and the dot is the front of the arrow. And we fire an electron into this thing. Okay, it's moving straight. And then once it goes in, it actually goes in a circular path. Now, this is just similar to your left-hand Fleming's rule, but remember, the current is actually the other way. So to find the force on this thing, we use our left-hand Fleming's, remember FBI, and we'll find that the force is pushing downwards. And so that means once it's inside the field, it will go in a circular path, okay, and then head out straight. Sometimes you can actually capture them inside the magnetic field and they get stuck in there. So as remember, this is circular. So simply, a cathode ray oscilloscope is something that we use more often. It's very similar to like a TV. Okay, and what we have at the back here, we have a heater coil. So this thing here is a heater, and so remember that is your coil, which once it's hot gives off electrons. Okay, so this once it's hot, and then we have a cathode, a grid, and a couple of anodes. Okay, or usually just in this case just one. Okay, so what happens? This cathode will have, let's say, electron gets to here, it gets repelled. Okay, but it actually gets attracted to this. Okay, so it gets repelled from that one and attracted to this one. Now you notice that there's a small gap in this one here, and there's also a small gap there, and that's to get rid of the wayward ones and also reduce the number of electrons that go through. And then we have a couple of plates. Now these plates here, so this one here and this one, they will control the motion of the electron up and down. And these ones here will be controlling it left and right. Okay, and it does that by electric fields. Now what does it hit at the end? It's the fluorescent screen. So the actual kinetic energy of the electrons, so energy kinetic, gets converted into light energy. And I suppose a bit of heat. There's always heat. And the last thing is the use of the CRO, and what you can use is an AC/DC voltmeter and displaying waveforms. Okay, effectively, if you had a microphone and you connected it, that would actually produce a varying voltage over time. Okay, if someone spoke into it. So this is what a CRO looks like. Generally, it's the screen that is the most important thing. There are two dials that are important. One is called the time base, and one is called the y-axis or volts per division, something like that. Okay. Now, this is a graph. Let's put in some axes. So there's your x and y. Now, the y-axis is volts per and some sort of measurement, and the x-axis is time in some measurement. Okay, and let's say we had a time of 4 milliseconds, and it's per centimeter. Then every one of these centimeter divisions is going to be 4 milliseconds. If the volts was measured in 1 volt per centimeter, then every one of these centimeters going up will be 1 volt. Okay, so if we had some sort of wave on here, and it went along like this, and we wanted to measure, let's say, the time from here to here, then we look at this scale. It's 4 milliseconds every division, so we got 1, 2, 3, 4 divisions, so that makes 4 times 4 milliseconds, so that equals, oops, what am I doing? So 4, 4 is 16 milliseconds. Okay. Now, height. Well, each one of these divisions is 1 volt, so we got 3 volts in amplitude. So, how about we do an example? A CRO has a calibrated time base of 5 milliseconds per centimeter, and AC signal is connected to it. What is the AC frequency? Okay, so every one of these squares is 5 milliseconds. Okay, so going across, you have 5 milliseconds each time. And so if we go 1, 2, 3, 4 from crest to crest, so there's 4 times 5 milliseconds, so that equals 20 milliseconds is the time for one cycle, or 0.02 seconds. Therefore, the number of completed cycles every second is the inverse of that, so it's 1 over the period. So that equals 1 divided by 0.02, which equals 50 Hertz. And that's actually the same as what's in our power supply on the wall.